Okay. I know. You're all like, blank screen. Okay, here I am. Hi. You'll see me, you'll hear me, no one's screen is still blank. We're all good, right? Great. Good. Okay. So, sorry for the bit of a rush getting fired up here tonight. I was a little behind, but got you the slides, and today we are going to do geometry. And this was one of the most important skill builders. In fact, this week was kind of skill builder week, because if you ask me which two skill builders are the most indispensable to their lessons, I would say, sentence correction and geometry. For both of these, if you don't have the fundamentals, it's really hard to get a lot out of it. So how was it for everyone? How was the skill builder? All right, good. It was fine, not bad. Okay. Anything in particular that people struggled with and want to maybe get a little extra attention on? Oh, yeah, see, they did that too. They did that in my high school. I went to like a magnet high school. It's for all like the smartest kids, and they still made like the football coach, like the science teacher, the math teacher, stuff like that, because they just didn't have somebody who was like actually trained as a science teacher. And they're like, well, the football coach has to do something around here to justify being here other than coach football. Let's have him do science. How hard can it be, It was awful. It was terrible. I'm so sorry. I feel... I have lots of thoughts about the American education system, but I'm going to try to keep most of them to myself. Anyway, there going to be any trick questions involving diameters and chords. There are tricky questions on this test, Matt. There are questions that are difficult, that reward your cleverness. But I would think that the people who write this test would say, and I would agree, that there's nothing that would qualify as a trick question. So certainly you should note that the diameter is a chord. It is actually the longest chord in a circle. But I don't think you should be worried about things that would be fairly described as trick questions at all. Okay? So certainly there may be some diameter and chord questions, but none of them will be trick questions in my view. Anything else? Coordinate geometry, several people. Okay, so we'll make sure that we talk about coordinate geometry. We are going to talk about it at the end. I'll see if I can hustle my way there and get there with a few extra minutes. Let me know at the very end if that worked out and if you feel better about coordinate geometry after we discuss it. All right? Okay. So, geometry on the GMAT, and actually kind of in the world, is really about two fundamental things. All right? And the first and foremost of them, geometry is about leveraging assets. Okay, it's about leveraging what you know about multiple shapes. Because pretty much every geometry problem is set up exactly the same way. And pretty much every geometry problem goes like this. There's almost always going to be at least one piece of information that they just give you. They say, here you go, here's something that I'm just going to tell you. Y minus x is 100. Or, the area of that triangle is root 243. Or, that angle is 60 degrees, or whatever, but they'll just hand you some stuff, And that stuff that they hand you will never be enough. If you could get there just with the stuff that they gave you, it wouldn't really be a geometry problem at all. It would just be like an algebra problem or something, maybe arithmetic, I don't know. But certainly not geometry. So for every geometry problem, there's something else that you've got to do, and that is there's always going to be at least one other piece of information that you have to leverage from your understanding of the fundamentals of geometry. There's something that you have to know that was in that skill builder, some basic principle that you need to be able to put out there and then rub that together with the thing that they gave you. And when you rub those two things together, the thing that they gave you and the thing that you know from the fundamentals of geometry, out will pop a genie. No, that would be great. Sorry, not a genie. Weird blue Will Smith. No, not even that. Just actually mostly an algebra problem. So, yeah, for all of you guys who are like, oh, thank God, finally done with that horrible algebra stuff. I'm never going to think of that again. Oh, gosh, guys, I'm sorry. I got some bad news. Thanks, Don. My jokes are going to be even more terrible than usual tonight. I'm actually going to tell what I consider the literal worst joke that I know. later this evening, so hang around for that exciting detail. Anyway, just an algebra problem, and if you were thinking, oh thank God, I'm finally free of that horrible algebra stuff, I got some bad news for you. You're not. You're never going to be, as long as you're taking the GMAT and really pretty much standardized tests in general. Algebra is the #1 most important math skill in this test, and it turns out that a lot of geometry problems are just layering for algebra problems in disguise. And of course, when we see word problems, same story. Data sufficiency, same story. Statistics, same story. A lot of these things are just layers on top of algebra. So sometimes people think they're bad at geometry, and they're not. You know, they're actually leveraging fine, they know the rules, they're using them properly, their visualization is good, but it turns out that they just suck at algebra. So if you're actually missing a lot of these problems, make sure you really inquire into why you're missing them and figure out whether it's actually a geometry problem you're having or perhaps an algebra one, because it could be either. Okay, so that's what this is about in terms of strategy, leveraging and layering. And I understand if everything I just said is a little abstract, so I think what I kind of want to do here is start us off with a problem so that we can all see what I'm talking about, and perhaps even put it into practice if we're good. And then we'll go from there. We'll have a discussion about that, and then we'll move on to talking about some of the different shapes we need to know. One thing before I give you the problem. In every one of these problems, as I've said, you're going to need to leverage something you know from the skill builder, something you know about the fundamental rules of geometry. Now, I hope that everyone has really mastered that skill builder, but in case you haven't, I will also say this. If for any reason you don't have that skill builder down pat, feel free today to go back into that skill builder and look up the rule that you need rather than sit there and kind of stare blankly at a problem. I don't want anyone to just basically not learn tonight because they didn't know the rules. In fact, if you look in the books or the ebooks on pages 59 and 60, we've collected for you a nice single cheat sheet of everything you need to know fundamentally about the rules of geometry, and you can feel free to flip to that cheat sheet freely for the whole evening. Of course, every time you do that, do let that be a reminder. You will need to have that stuff memorized for test day because there will be no cheat sheets then. Okay? Great. So let's start off with a problem, as I was saying. Layering and leveraging. Let's see what you do. Okay, let's get some more answers in. This problem should not take more than 2 minutes, and yet I've only got 14 out of 23 answers. That is not good enough. Please, answers in. I'm going to close this poll in the next 5 seconds. There's the results. There's a closed poll. Okay, thanks. We did get a few more answers. We got up to 19 of the answers, so that's a lot better than 14, thanks to the 5 people who threw them in at the last minute. Now, I said that this problem is about the classic leveraging and layering, and it would be a great example to start with. And I think you guys did pretty well with this. At least more than half of you got this right. But the real key to this problem, as I see it, I think everybody probably knows what I can say about this angle here and what I can say about angles x and y. Go ahead and tell me, what can I say about angles x and y? Yeah, they equal 180, absolutely. Straight angles, 180 degrees. I assume that we're 23 for 23 on knowing that, right? Does every single person in here know that? Let me ask the other way around. Is anyone who didn't know that? Is there anyone at all who's like, no man, I didn't know that. And I couldn't look it up in the skill builder either, or the cheat sheet for some reason. I just could not figure that out. See, I don't think anybody's sitting there thinking that. So what it really boils down to for me is pretty simple. The people who write that down algebraically almost always get this right. The people who don't, who simply look at it and try to play guess the angles, it's kind of 50-50, all right? People try and play guess the angles. They're like, you know, 100 apart, so like 180 and 80. No, that didn't work. 100 versus 80, no, I don't know. They play random guess the angle games, and they lose those games. But the people who simply wrote down y plus x equals 180, and then wrote back down this statement, the thing that they gave us, remember one thing we know from geometry, one thing they gave us, rub them together, get a system. And I think anyone who's got this on their page and has any skill in algebra at all after what we've talked about, this is an easy peasy system, right? We've talked about how to do this, you know. And we solve this in our favorite way, which of course is elimination. So we add them up. The x's drop off. We end up with 2y is 280. Thoughts, Archana? At which point y is 140. And we can plug back in, get x is 40, z is also 40, opposite angles are equal. That's something else we've leveraged from geometry. And finally, one more thing we leveraged from geometry, the whole circuit all the way around this circle is 360. We've got 40 of that. We've got 40 out of the 360. That's 1/9 of the circle. Ding, ding, ding. Does anyone have any questions about this? Any thoughts? One thing I do want to highlight then, I want to say this. Notice that when we leveraged, we didn't just leverage random things we knew from geometry. In particular, we tried to leverage information about the same thing that they gave us information about. They told us about angles, so we leveraged angles. More specifically, they gave us an equation involving x and y, so I leveraged something involving x and y. And that is usually, not always, we'll talk about this more later, there are exceptions, but that is usually the right way to go. How come? Because you want to leverage and then get an algebra problem, and you want that algebra problem, when you get it, to be something you can actually solve. And if you leverage the same kind of information, you're going to get multiple equations, perhaps, that involve the same variables, which is a great thing when the time comes to solve them. So in general, try to leverage the same sort of information, even about the same unknowns, as the information they gave you, and usually that will make your life better. It certainly did here. Those of you who missed it, am I right about what happened? Did you have problems because you didn't write down x plus y equals 180, or did something else happen? Where did people go wrong? Because it's either that or, yeah, I mean, it's probably that. If not that, you just really had some problems with the system and solving in algebra. Oh, bummer. Yeah, 2 minutes. This problem is not something that should take longer than 2 minutes. If you're going from the word go, I actually think this is more like a 1 minute problem. But you gotta be on the ball. Sorry that that didn't work out for you, Tanvir. Anyone else with thoughts? Yeah, see, that's the thing. You gotta get to a point where you're comfortable enough with this that you're not spending the first minute kind of getting your bearings. You know, if you do, then you're gonna end up with that issue of at the end you're going to be really rushed and the mistakes start to creep in. So you want to practice these, and I know you haven't had the chance to yet, but you're going to want to practice these to a point where when you see something like this, you immediately know what to do and you just start doing it. So you'll get there. Yeah, 2y plus x plus z equals 360 is a little awkward. Makes it more complicated than it needs to be. It will work if you then say, okay, an x and z are the same thing, but it's more work than you need to put in. Okay, fair enough. So thank you for the comments, and let's keep moving. So, for the rest of the class, we're going to break it up by the different types of shapes, although in every case the emphasis is still going to be on strategy rather than on just sort of the foundational skill builder rules. And this is not a news flash at this point. This is not a shocker. But we are going to start with triangles, and triangles are the most important shapes, hands down, in geometry. The literal majority of the geometry problems that you see on your GMAT will involve triangles in one way or another, in all likelihood. I don't want to just say certainly, but 95% chance most of these things are going to have some triangles in them. Because first of all, a lot of them are just straight up triangle problems, but also a lot of the times when you're doing something that's ostensibly something else, you know, a quadrilateral problem, a problem involving a circle or coordinate geometry. A lot of those things are just layering. Some other polygon. Those are just layering, and it ends up being triangle problems in disguise. So it turns out that most of these, again, do come back to triangles. So you need to be very good with your fundamental rules. You need to know these better than anything else. And so here's the review of them. Obviously, you need to know the area of a triangle is 1/2 base times height. You need to know an isosceles triangle is at least 2 equal sides, at least 2 equal angles. Note the at least, that does mean that an equilateral triangle is a kind of isosceles triangle in the very all oaks are trees manner of thinking about it. Equilateral triangles are a special case of isosceles, and an equilateral triangle, of course, all 3 sides are the same, all the angles are the same, and they're all 60 degrees. You should, of course, know what a right triangle is. 90-degree angle. Opposite sides called the hypotenuse. The other sides are called legs. And you should know that for any right triangle, the Pythagorean theorem applies. And you should know what that is. A squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. A squared plus b squared is c squared for any right triangle. One more thing that I want to mention here. The book puts this in the you ought to know section, but I'm going to talk about it right now. I think this is very important. This is one that just it floors me how much people miss this. I'm always shocked to see, and I guess this just shows it's my own bias. It's not you, it's me. But I'm always shocked to see otherwise highly skilled, highly competent, high-scoring people miss triangle inequality questions. Because it's such a fundamental principle of triangles, and it's not that hard to apply once you know it. And yet people miss it all the time. The triangle inequality says that the sum of the lengths of any 2 sides of a triangle is greater than the length of the third side of that triangle. Do you understand why that is? Does that rule make sense intuitively to you? Yeah? Makes sense to Stephanie. Everyone? If you take away the squares? No, we're not talking about a right triangle. We're talking about, yeah, exactly, Rohan. Yeah, we're not talking about a right triangle. We're talking about any triangle. But Rohan, yeah, that's exactly why this is. What I like to tell people is, well, I guess it's kind of a question. But, have you ever seen a T-Rex holding hands with itself? Like, you ever seen that? Have you? You haven't, right? You know why you haven't? Because they're extinct. Hey, I'm not judging the poor guys. I'm just saying, like, they can't hold hands with themselves because they are extinct. And also, because they can't reach, they have short arms, like, or they just can't do it, And that's what no, that was not the worst joke for today, Artana. It gets worse. And that's what I'm talking about with the triangle inequality. This is not a triangle. Why? Because it can't reach. It's not a triangle. It's a T-Rex trying to hold hands with itself. Don't make your triangles be T-Rexes trying to hold hands with themselves, okay? Because they don't exist. Look, whatever ridiculous story I can tell, whatever ridiculous image is going to make this stick in your brain, if you remember it, yeah, then it's good. So, Rohan, this rule, as I've stated it, covers everything because it says the sum of the lengths of any two sides must be greater than the length of the third side. Now, you can show that that also means that the difference of any two sides, the third side has to be greater than the difference. You can show that too, but that's actually just equivalent to this rule. As long as you check that the sum of the two lengths of any two sides is greater than the third, then you've actually covered everything, as long as you check it for each pair of sides. Yeah, okay. So these rules give rise to a few things we call special triangles. And these were in the skill builder, so this is a quick skill builder review, but please make absolutely certain you've got these down pat. It's just like I said last week when I talked about special quadratics, and what I basically said was, look, you know they're going to be on your test. And yeah, you could sit there on your test and you could work them out from scratch, but why would you do that to yourself? You know, why not just memorize them in advance so when they inevitably come up, you're ready with the answer in hand? And the same thing is true here. These triangles will be on your test. So why not just go ahead and memorize them right now and have them like the back of your hand so that when they come up on the test, you're like, I got it. I'm all set. So there's 3 or 4 types depending on how you count. The first 2 or 1, depending whether you want to group them together or not, would be your Pythagorean triples. You should note that there are integer solutions to the Pythagorean theorem. For right triangles, there are some integer valued sides that satisfy a squared plus b squared equals c squared. The first and smallest Pythagorean triple is 3, 4, 5. 3 squared is 9, 4 squared is 16. Add them up, get 25. That is sure enough 5 squared. You should also note that any multiple of a triple is itself a triple. So if 3, 4, 5 is a triple, and it is, then so is 6, 8, 10. So is 9, 12, 15. So is 300, 400, 500. Any multiple of a triple is a triple. But you should also be aware that there are, in fact, infinitely many distinct triples. There are infinitely many triples that are not just multiples of 3, 4, 5 or multiples of one another. And the next larger distinct triple, the next one that's not a multiple of 3, 4, 5, is 5, 12, 13. 5 squared is 25, 12 squared is 144. Add them up, you get 169, and sure enough, 13 squared. Please memorize 3, 4, 5 and be able to recognize its multiples. The GMAT loves to test multiples like 6, 8, 10 and 9, 12, 15 and 15, 20, 25. I would also like you to memorize 5, 12, 13 because I've seen it tested multiple times, but I will not ask you to memorize anything else as Pythagorean triples are concerned. I know there are other triples out there. I don't need you to know, 9, 40, 41 or anything like that. It's a triple. I don't care. I don't need you to even know multiples of 5, 12, 13. I've never really seen them test 10, 24, 26, or any of the other multiples of 5, 12, 13. So if you know 3, 4, 5 and multiples, 5, 12, 13, no multiples, that's enough for the triples. And then you've got your other 2 kinds of special triangles. You've got your x, x, x root 2, 45, 45, 90 isosceles right triangle. And you've got your x, x root 3, 2x, 30, 60, 90 special right triangle. And here's some art. You should know these pictures. If I start with a square, and all the side lengths are x, and I cut that square in half diagonally, then these angles become 45 and 45 because it's an isosceles triangle and the opposite angles have to be equal. And furthermore, you could use the Pythagorean theorem to show, but frankly, please just memorize. The hypotenuse of that triangle, the diagonal of the square, is x root 2. Please memorize every aspect of this picture. All of the lengths, all of the angles, the fact that it's half of a square, everything. Now if I take an equilateral triangle, all of the sides of which are the same, and if I choose to call the sides 2x, 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 and that would also be 2x, and if I cut that equilateral triangle in half vertically, then I again get some special triangles. I get some right triangles. And since I've cut it in half, these angles each become 30. And this 2x at the bottom becomes x and x. It's very grayed out here, but that's x also, and the whole thing would have been 2x. And finally, you can use the Pythagorean theorem to get, although again, I just want you to memorize the height is x root 3. And this gives rise to my 30, 60, 90, x root 3, 2x special right triangle. And again, I want you to memorize all of this. I want you to memorize all of the lengths. I want you to memorize all of the angles. I want you to memorize that it's half of an equilateral triangle cut vertically. Everything. Okay? This is very important. One side note here. It is true that when I dropped the height in this triangle, I bisected it. I cut it into 2 equal pieces. However, that is not always true as a general matter. In fact, it turns out that when you drop a height in a triangle, you will bisect the triangle if and only if that height drops between 2 equal length sides. If it doesn't, then you are definitely not bisecting. You drop this height in this triangle, these angles are not equal. These lengths are not equal, okay? When you drop a height in a triangle, it will bisect if and only if those 2 sides are the same. So just make sure you know that, because otherwise people get very carried away with this. They start dropping heights everywhere and going, bisecting, 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 and they're wrong. So don't do that. Any questions about special triangles? This is Skill Builder review, so hopefully not, but if you have them, now's a good time to ask them. Okay, well you can guess what time it is now then. It's problem time. Polls opening. Let's see what we've got here, guys. Get some answers in. I'm still waiting on a bunch of people. I'm going to close this poll now. Okay. So again, one thing they gave us, they literally told me the area. One thing I know from geometry. Gee, what do I know from geometry? I feel like I just had a picture that I knew about this. Something like, oh, that picture. Yeah, it's there again. Huh. Okay, so I know that my triangle looks like this. If I call the side length 2x, and by the way, do be careful with this. As I've set this picture up, the side length is not x, the side length is 2x. So if you're going to use this, then make sure that when you get x, you don't think it's the side length, and make sure you recognize you're actually looking for 2x instead. But now I could use this to get the area, because we all know that the area of a triangle is 1/2 base times height. And of course, the base is 2x, the base of the whole triangle, right? And the height is x root 3. So 1/2 times 2x times x root 3, which is, in other words, x squared root 3. So take the thing that they gave you, take the thing that you know from geometry, rub together. And there you go. I've now rubbed them together and said, well, if they're both the area, they're equal to each other. So root 243 is x squared root 3. This is no longer a geometry problem. This is now an algebra problem involving exponents and roots. Now, there are many ways to solve and simplify this problem, and so if you didn't do exactly what I did, that's okay. But me, I'm thinking back to my process for exponents and roots, and what I said is I'd like to start by prime factoring my bases. So I start pulling apart 243, and I note that root 243 is definitely going to have a 3 in there, right? Because the sum of digits is 9. I could also divide out a 9, but it feels like it'd be harder to divide by 9 and easy to divide by 3. So I pull out a 3, and 3 goes into 24 8 times, and 3 goes into 3 1 time. No real carrying there. 81. Oh, wait, I know the root of 81. That's 9. So I'm left with 9 root 3. And I can replace this with 9 root 3. 9 root 3 is x squared root 3, so 9 is x squared, so x is 3. Finally, don't forget, x is not the side length. The side length is 2x, so it's 6. Of course, they didn't ask for the side length either. They asked for the perimeter, which is 18. Chloe? Can you show how you got a plus a equals x squared square root 3? Yes, I can show that. So again, the area of the triangle is 1/2 base times height. That's the base, that's the height. 1/2 base times height. Right? And then from there, note that the 1/2 and the 2 cancel out. And so I'm left with simply x squared root 3. Do you follow that, Chloe? Does that make sense? Okay. Look, if you have questions, it's fine. You know, I'm happy to spend a little more time here if anyone needs it. So thank you for speaking up, certainly. And that goes for everyone. If you have questions, if you're unsure, you know, you did the right thing, speak up, let's talk about it. Okay. So what are your thoughts overall on this? Because I only had 10 people out of 23 who actually got this right answer. So what about the rest of you? Did you have trouble with the geometry? Did you have trouble with the algebra? Was it just pacing? What was it? So Gabriella needed to remember the triangle picture. That's essentially a geometry point. You'll get that with practice. Stephanie got caught on the algebra. David had time. Okay, so some of everything. Yeah, so just need a little more practice. Yeah, okay. If you just didn't quite have the time, then you're going to want to look at where that time went. Did you kind of take a long time to figure out the picture? Did you kind of take a long time to get the area formula from that picture? Did you take a long time to knock down the algebra once you got there? You know, and then just work on that and get it faster, and you'll be okay. Oh, yeah, the height is the x squared root 3 in that picture. The height is always at a right angle to the base, so the height is not necessarily a side of the triangle. In fact, it's only a side of the triangle if you're looking at a right triangle. Otherwise, it's not. Okay, any other thoughts here, questions or comments? Okay. Maybe a flat 600, I don't know. It's perhaps a bit above average. Maybe it's even a 550 and it's average. It's certainly not a 700 level problem. I'd be shocked if this was anywhere around 700. So it's not easy, but with practice, this is your bread and butter problem that you should be crushing. You should be looking at this like, thank you, GMAT gods, for giving me such a nice, straightforward geometry problem. It takes practice to get there, though, I know that. Chloe? Chloe and Daniel are typing. I'll give them a minute. Chloe and Daniel are both typing books, apparently. Okay. I'm going to flip the page, but if you guys want to continue, I would be happy to hear your comments. I just don't want to kind of stand and stare blankly. So please, please, let me know, because now I'm deathly curious what you were typing all this time. So don't delete it. I want to know. Okay. Certainly, though, you could have memorized the formula, right? So that's what Daniel was asking about, as it turns out. Yeah, I mean, that's basically what this is. X squared root 3 is the same as side squared root 3 over 4 because x is half the side length. So look, the formula from the skill builder and the one that I gave you are equivalent. They're the same formula. The formula is x is half the side length, right? X is side over 2. But when you square that, if I wanted, and I never use it in that form, but then when you distribute the square, side over 2 quantity squared would be side squared over 4. Sorry, guest entering the room. Do you follow that? So again, like, I don't care. You can use this form. You can use that form. It should work either way, though. So like, if you like the skill builder form, you just want to use that, just do it. It's fine. Chloe, is that clear? Daniel, you too? Okay. Chloe? Yeah. Okay, great. So let's move on. I'm going to skip that problem, actually. So I want to talk about this problem together. Okay, so don't jump in and do it yet, because we're going to discuss this together, and for a couple reasons. For one of them, it's kind of a train wreck when I just tell people, go do it. It doesn't go well, in my experience. You know, it's really important to leverage your assets in geometry problems, and it's really important to do that early in the game. One of the mistakes that a lot of people make in geometry is they don't leverage their assets enough early enough in the problem. And you know, because of that, they end up kind of having to backtrack and go back for more information, and it just makes their lives harder, it's more confusing. This is doubly true when you get a data sufficiency problem, because when we talk about data sufficiency next week, one of the things we're going to say is that it's also about leveraging assets. And so if that makes it sound like a data sufficiency geometry problem is pretty much the leveragiest problem that ever leveraged, well, yeah, you'd be right, okay? So in this problem, what I want us to do is I want us to go through together and just work on leveraging and see how much we can pull out of this problem without going to the additional statements. Now, the thing about that is, it can feel very slow. You're spending all this time without even going and looking at the additional statements, and you're like, oh my god, I'm almost 2 minutes in, I haven't even looked at statement 1 yet. Are you kidding? But the thing is, a lot of times when you do that, it's incredibly fast when you finally get to the additional statements, and it pays off double. Because otherwise, if you'd gone to the statements right away, you'd have to leverage all that information with statement 1, you'd have to leverage all of it again with statement 2, and God forbid the answer C, you might have to leverage all a third time. But if you do it up front, you do it right, you do it once, and then you just plug each statement into it, you actually pay that time off double or triple on the back end. But one other thing before we start leveraging here, does anyone else hate this 3-letter notation here? This whole AED, ABE, whatever? It's so confusing, isn't it? Like, it's just hard to read. You know, I don't ever want to call, and then, you know, it's tedious to write it into the equations, be like AED plus 2 times ABE or whatever. I don't know what the equation's going to be, but whatever it is. It's awful. Plus, on top of all that, I simply never want to call any angle bay. Yo, dog, that angle's bay, right? Like, man, you know, it's bay. I'm not doing that, okay? So We're going to relabel these angles. Frankly, I'm just fine with using, just English letters, standard, Latin alphabet. But I'm just going to call the angle some things. Yeah, certainly not fun for dyslexics. I imagine that would be awful. So I'm just going to label these things. Okay, so I'm going to call that x, that's going to be y, z, v, and w. Now don't worry about whether you can remember all that off the top of your head because I've conveniently put them in the slides. So that's going to be x, y, z, v, and w. And now I can reword the entire problem. And you'll see how much easier it becomes to read and parse when you reword it. So what is the question asking? In terms of the new variables I've got, what is actually the question here? Yes, that's right. X minus y. This is angle x. That is angle y. Okay? Now, I've asked this before and had people actually miss that. It really is tricky with this. But now I'm going to reword the question like so. What is x minus y? That's the question. Statement 1 tells me w is 30. Statement 2 is y plus z is 150. But let's put aside the additional statements for a minute. Because now what I want to do is I want some of you to tell me just one. Just each person can just give me one basic fundamental thing I can leverage from this problem, one relationship among some of these angles. Nothing fancy. Give me one. Sure, yeah. I'll give you credit for that. This is also 90 because the straight angle is 180. Matt says w plus v plus y is 90. Very good, Matt, because what you're saying is w plus v plus y plus the 90 right there is 180. So w plus v plus y is in fact 90. Very good, because the triangle adds up to 180. Chloe says x plus z is 180 because it's a straight angle. Yep, I'll give you that one. Very good, Chloe. Continuing down the list, who else did I see next? Patrick gave me x plus z. Oh, sorry. Chloe beat you to it. So there's a couple more. Who's got something else? Somebody different? Give me a different one. And if you've already given me one, yeah, Chloe's a speed demon there. Good job, Chloe. Cameron gives me v plus x is 90. Right, because v and x and 90 makes 180. So x plus v is 90. There's one more. There's one more. Z equals E? No. Careful. And by the way, if you already gave me one, don't give me another. But be careful with this, okay? A common mistake that people will make is they assume things like, oh, I assume this triangle is equilateral, or isosceles. I assume there's a 30, 60, 90, or a 45, 45, 90 here. My policy on all of these things is very simple. My policy is, if you can't prove it, you can't use it. Don't get caught assuming about triangles, because frankly, you know nothing about where point C is. It looks like point C is here, but actually, maybe point C is way over here. And angle E looks nothing like angle Z. And this triangle is not at all isosceles or equilateral or 30, 60, 90 or any of it. So don't assume that. If you're saying this is that, I don't buy it. What else have we got? Y plus Z plus W. Oh, oops. Yes, that was the fourth one. Z plus Y plus Z plus W is this triangle, adds up to 180. Okay, so accidentally turned the page to exactly where I was trying to get to anyway, so that worked out all right. But that's the four of them. Now, one thing I want to impress upon you is that we are not, by any means, tasked to know a bunch of esoteric, complex, geometric theorems. What did we use to get to this point? A straight angle is 180 degrees. A triangle adds up to 180 degrees. A different triangle adds up to 180 degrees. A different triangle adds up to 180 degrees. That's it. The only geometric principles we've used so far is triangle equals 180 and straight angle equals 180, which I would venture to say all 23 of you know without any difficulty at all. And that allows us to write down these four algebraic statements. Okay. Now, the question asks for x minus y. How could I use some of these statements to get something that looks more like that, to get something that's like x minus y. Ah, elimination. I love elimination, Alex. It's like my favorite thing to do with systems of equations, so I'm really happy you said that. You said eliminate the first two. I just take the first two equations. I could just straight up subtract them. The z's would cancel. I would get x minus y. The 180s would also cancel. I get x minus y minus w equals 0. Now you'll note I could have done the same thing with the latter pair of equations as well, and that would give me actually the exact same thing, as you can see right here. I can take either pair, and I can eliminate x minus y minus w minus x minus y minus w equals 0. So you can add the w across and find out x minus y equals w. So they say the question is what is x minus y, but what's the real question? What are they really asking? They really just want w. That's all the real question is. So now look, I've been on this problem for a while, I've done all this work, I'm running out of time, and now I think I've done as much as I possibly can without going to the additional statements. So now, as the time ticks away, I'm going to very quickly look at statement 1, and is it sufficient? Yeah, of course, statement 1 literally gives me w, which is exactly what they asked me for. And then statement 2 gives me y plus z, which of course one step away indirectly gives me w, since, you know, y plus z plus w is 180. So if y plus z is 150, w is 30, which is the same thing that statement 1 gave me. So D is the correct answer. And that's how you do this problem, by leveraging your assets. And that's the right way. What are your thoughts? It is a lot of work in a short time. I will also say a couple of these problems, like some of the word problems that we'll see later, can end up being longer. Some of these longer geometry problems are more like 3-minute problems. If this took you 3 minutes, I think I wouldn't kill you for it. As it turns out, though, you didn't actually need to get all 4 equations. You could have just settled for 2 if you got the right 2. How did I get blank plus blank equals 90? This one? Y plus v plus w is 90. That one done? If you look at the big triangle, there are 4 angles that make up the big triangle. Y, w, v, and this 90 right here. So that means y plus v plus w plus that 90 equals 180. And that's how I got that. We simply took each of the 3 triangles on the left-hand side, because again, we don't know anything about the right-hand side, but we took each of the 3 triangles on the left-hand side and used the fact they had a 180. How is the second statement sufficient? Well, then let me ask you this. If y plus z is 150, what's w? Look at this triangle right here. If y plus z is 150, what is w? Which is the same thing statement 1 gave me, and obviously we've already decided statement 1 is sufficient, so statement 2 is also. Is that clear, then? Yeah. Okay, anyone else? Any other thoughts here? Any other questions or comments? All right. So far, we've been leveraging, and pretty much every problem we've seen, we've leveraged the same kind of information as what they gave us. And that will generally be true, and it'll go back to being true for most of the rest of the class. And I say go back to because there are exceptions, okay? And occasionally, maybe 10% of the time, at the higher levels, you're going to see a problem that involves a lot of misdirection, where the thing that you need to leverage is simply not the thing that is most obvious, that is most clearly related to what they gave you. normally you get something about angles, you leverage angles. You need something about lengths, you leverage lengths. They tell you about area, you leverage what you know about area. But if you try that and it's not really working, it's either getting very, very, very difficult and long and ugly, or just flatly it does not solve the problem. Before you throw up your hands and say, woe is me, take a step back, take an extra minute, and ask a simple question. What else could I leverage about this problem? What else is there to know from geometry about this figure? Even if, I look at it and it's not immediately obvious how that's useful. Just go ahead and get it anyway. Because sometimes what you really need for these problems is just to get a different perspective. And if you get a different perspective, sometimes you'll find out that the answer you needed was just in the last place that you would have thought to look. Okay? So I'm going to tell you something about this next problem. I know you guys love to hear when I fail and struggle with things because, I'm not perfect and I've had my own hard times with problems. And this next problem is a wonderful example of that. I remember the first time I did it and I found the worst possible way. Because I looked at it and I said, well, the obvious thing to leverage is blank. Maybe it'll be the obvious thing for you, but maybe it won't. I don't know. But what was obvious for me ended up being a very bad choice. It got awful. And I ended up sitting there, being a stubborn idiot, and fighting it for like 3 minutes. And after 3 minutes of a lot of really hard work and really messy algebra, I did finally manage to solve the problem and get the right answer. Yay for me. And then I turned the page and looked at the solution and went, oh my God, I'm so dumb. Because if I had just been able to get the right perspective on this next problem, everything would have been so much easier. So I hope you'll get the good perspective, but I imagine some of you, after the next couple minutes, are going to end up having the same experience I did. When you see the good way to solve this problem, you're going to end up feeling really annoyed. Let's say that. You'll feel really annoyed by the good solution to this next problem, okay? But we'll let you try it first. And here it is. Don't be scared. It's okay. I'm going to give you an extra second here because I've got people still trickling in some answers, but I would love to see a few more. I got 15 answers out of 23 people. Anyone else? 16 answers? Okay, time to close it up. There you go. Now, some of you are about to feel very smart and others are about to feel very stupid. If it's any consolation, when I did this problem, I ended up feeling very stupid. So at worst, you're not alone, okay? But I am going to show 3 ways to do this problem in decreasing order of stupidity, all right? The first one, of course, is the way that I originally did this problem, and I hope you'll agree that I'm dumb. And this is a bad way to do it. So don't do what I did, people. Be better. Look, one thing you could do. Well, first of all, no matter what you do, you need to recognize the hypotenuse is 5, right? 3, 4, everyone says 5 altogether, right? But since they ask you for a length, I looked at this problem and said, well, you want a length. I should leverage what I know about lengths. And it's a right triangle. In fact, there's lots of right triangles. And if you say the words length and right triangle to me, I immediately free associate Pythagorean theorem. So I'm like, okay, I'm going to do the Pythagorean theorem. And of course you say, well, yeah, but how you do the Pythagorean theorem with little triangles, you don't know the other side. And I said, well, that never stopped me before. I'm going to label my unknown. I'll call it a variable. Call that y. Call this 5 minus y. And when I do that, I can do the Pythagorean theorem on each of the small triangles. On this one, x squared plus 5 minus y, quantity squared, equals 16. On that one, x squared plus y squared equals 9. Oops. Board is very sensitive. X squared plus y squared equals 9. And I can write down that system, and I can say, oh, that's solvable. You know, I can FOIL out the quadratic, and it's x squared. Well, I guess I subtracted first here, but I could subtract them, cancel out the x squareds, and then I can FOIL out the quadratic. When I FOIL out the quadratic, y squared minus 10y plus 25, but then minus the y squared, and the y squareds cancel out. I get minus 10y equals minus 18, and I can divide by minus 10. Y is 18 over 10, which is 9/5. And now I just have to plug back in and get x. X squared plus y squared is 9, and of course x squared plus 9/5 squared is 9. And 9/5 squared is 81 over 25, and the common denominator of 25 makes this 9 becomes 225 over 25. And I finally subtracted. X squared equals 225 over 25 minus 81 over 25 is 144 minus 144 over 25. And x is 12/5. Oh my God. Okay. So I did it. Hooray. What do you think? Is that a great way? Are we all excited to solve this problem in this way? Oh, that was a terrible idea, and I'm really ashamed of myself. It does work, but at some point there, after like the first step or two, I should have taken a look at that and gone, you know what? Nah, this got to be a better way than this. This is no way. And if I had said that, if I had stepped back and looked for the better way, I might have actually found one. What else could I leverage besides lengths? Because I was trying to leverage lengths since they asked me for a length, but it really didn't work out. What else could I leverage? Well, that just seems dumb, Azhar. You said area, and so does Archana. Several of you said, I don't know what that has to do with anything. So I'm going to come back to that. But what else? I got area, maybe. Yeah, okay. Shh. What else? Uh-oh. Hold on. I like what Gabriella said, but David, I'm sorry, I hate what you said. Where's the 45, 45, 90 here? PRS is not 45, 45, 90. This is a common mistake of people who got this problem wrong. A lot of people assume that this line bisects this angle and that these are 45 degrees. Those people are incorrect. In fact, I know for a fact it does not bisect, because in order for this height to bisect, and it is a height, it's at a right angle to one side of the triangle, so it's a height. In order for it to bisect, these two sides would have to be equal, the 3 and the 4, but they're not equal. And therefore, this line PR does not bisect those angles, And those angles are not 45 degrees. So I'm all for leveraging angles, but I'm very opposed to the guessing of the special triangles. And look, I'm making an example of this because you're not alone. Every time I do this, a whole bunch of people guess 45, 45, 90. And then often when I tell them it's not that, they say, okay, so it's 30, 60, 90. And guess what? It's not that either. Okay? So was there anyone else who wrongly assumed things about these angles, that they were 30, 60, 90 or 45, 45, 90? Anyone else assume something like that and willing to admit it? Yeah. See, you're never going to be alone in that, David. Lots of people do. Yeah, Rupesh as well. Okay. So look, it's all right, but learn from it. Don't assume special triangles, because here, you're wrong. And if you assume, sometimes you'll be right. But do you really want to coin flip on these problems? Because that's what you're getting. Okay. But I could leverage angles. Gabrielle is not wrong about that. It's just that I don't know them. But wait, that's never stopped me before. When I don't know something, I label an unknown and I proceed with a variable. So let's call this angle A. What is this angle in terms of A? This one right here. Yes, Tanvir, that is correct. That angle is 90 minus A, because A plus 90 plus this angle is 180. And so that angle is 90 minus A. What is this angle? This one right here. Yes, because they add up to 90, so that angle is again A. Finally, what is this angle right here? Not isosceles. That's 90 minus A, because it adds up with A to make 90. So Stephanie's correct. Do you all follow all of those angles? Do you all understand why they are what I say they are? Do you notice anything interesting about those angles? What do you notice? Yes, that's right. All of the angles of each of these three triangles are the same. The triangle on the top left has angles A, 90 minus A, and 90. Bottom right, A, 90 minus A, and 90. The big triangle, A, 90 minus A, and 90. These are actually all the same triangle, just scaled up or down by a constant ratio. We call that similar triangles. And I can use that similarity idea to get my answer. I'm going to work with one of the small triangles and the big triangle, mainly because I know all of the side lengths of the big triangle, so it'll be easy to work with. So let us consider, let's see, which triangle do I want to consider? PQR. Let us consider PQR. What is across from A in PQR? What is the side across from A in triangle PQR? X. And what is the side across from A in the big triangle? Four. Good. What's the hypotenuse? So X is to 4. What's the hypotenuse of the small triangle? 3. And what's the hypotenuse of the big one? No, the really big one. So do you agree that X is to 4 as 3 is to 5? So X is 12/5. And hey, I got there again in a totally different way. Was this better than the last way? Was this better than option number 1? Okay, much better. But still a little hard, right? Okay, so let me now humor all you weirdos who were trying to get me to do area. That just seems stupid, because like area has nothing to do with this problem, so whatever, man, but like I'm gonna humor you anyway because I'm so nice, right? I'm really being nice right now. So what's the area of this triangle? Oops. What's the area of this triangle? Oh, okay, too late. It's 6, right? We all know the area is 6. 1/2 base times height. That's very simple. Do you all see that? Okay, so you remember how at the start of this problem I said that sometimes you just need to get a different perspective? That's kind of a little inside joke that I have just with myself, because I meant literally. And I would now like us all to get a literally different perspective on this problem. So pick up your computer monitor and just turn it, or I'll just pick mine up. Nope, too heavy. You know what? Forget that. I'm just going to turn it by magic. And I'm going to turn the triangle about like this. Now, what's the area of this triangle? Oh, it didn't change when I turned it, huh? Interesting. Okay, what's the base of this triangle? It's making me dizzy. 5. What's the height of this triangle? X. So using the area formula then, the area is 1/2 base times height. And of course that equals 6. So 1/2 times 5 times x is 6, and x is 12/5. Now how was that? Was that easier? You all feel stupid now? It's okay, again, I felt stupid too, so this is the easy way. It is, right? It's like black magic. I looked at it and I was like, oh, you have got to be freaking kidding me. Are you serious that's the solution? I was so mad. I was so mad. Because remember, I did solution number 1 and it was just miserable. Oh, Tanvir, it's okay, it's all right, we're learning, okay? I'm in here to teach you all the things you don't know how to do, not all the things you do know how to do. If you came in here and you felt super smart, that'd be a problem, right? If you came in here and you could do everything I was teaching you, you wouldn't want that. This is better. Yeah, but you wouldn't get anything for your money. You wouldn't learn anything. You would never be any better than you were. If you walked in here and you already knew everything I was teaching, what'd you spend all that money on? What'd you spend all that time on? You want to come in here and get your ass kicked. Trust me, this is better for you, and it's better for all of you. I'm here to kick all your asses so that this test won't. Don't feel bad about yourself. Just don't get down on yourself, okay? Like, I really want you to understand, like, I try so hard to make sure that you know that I'm not judging you. I even joke about it, like I play at it. Like even here when I'm going, oh, that's so stupid. You know I'm kidding. Totally kidding. Because it's very simple. I want you to know that it's okay to do stupid things sometimes. I do it, we all do, as long as you learn. Where did this 6 come from, Daniel? That's an excellent question. Let me unturn the page. The area of the triangle is 1/2 base height, right? So the base is 4, the height is 3. 1/2 times 4 times 3 is 6. Agreed with that, Daniel? Do you agree with this 6 at least? Thank you, Stu, I think. I'm not sure if that's a compliment. And of course the point is, yes, if the area looks like 6 like this, then it still looks like 6 when it's this way. Alrighty, so mental flexibility is important. If you get stuck doing it one way and it happens to be a bad one, you might end up regretting it. So if it starts to look like you've gone down a bad path, that's okay. But step back and say, what else could I look at? How else could I approach this? What's another perspective I could get? Because there's almost certainly a better way out there somewhere. There's always a better way. Now, one thing we did see briefly in this problem is we saw that similarity could be a useful tool for us to solve this problem. And I'd like to spend a little more time there, because the skill builder says basically nothing about similarity, so I think we ought to talk about it, and I think now is a good time. Okay? Similarity is not just for triangles. I'm talking about it in triangles because it's often tested here and because it's easiest to visualize with triangles. But understand that any geometric figures can be similar if simply two geometric figures are the same shape, just scaled up or down by a constant ratio. In fact, some geometric figures are all similar, always. Every circle is the same as every other circle. There's only one circle in the universe, right? It's not like you ever see a circle and you're like, oh, that one's different shaped than the others. Then it's not a circle. All circles are similar to all other circles. All squares are similar to all other squares. But not all triangles are similar to all other triangles. Now, if you get similarity, if you can prove it, then you get a lot. Similarity is very, very powerful. Okay? It does many things for you. So the first thing I want to do is I want to tell you what you get if you buy some similarity. And then we can talk about how you can actually get some similarity for yourself. All right? So, if you buy some similarity, the first thing you get is you get all of the corresponding angles between the two figures are equal. Angle A in the little figure, angle A in the big figure, same angle. Angle B in each figure, same. Angle C in each figure, the same. All of the corresponding angles are equal. But it's not just that. You also get a constant length ratio. The ratio of sides from one to the other is the same for each corresponding pair of sides. And not just sides, but also perimeters, also height. You get it all. You get every single possible length that you could compare between the two will have this exact same ratio that we generally use the Greek letter phi to represent. That's phi, by the way, in case you weren't into the Greek life in college. Okay. But wait, as they say in the business, there's more. Because if you act right now, I'm not just going to give you the length ratio for the same price, I'm also going to throw in an area ratio. And the area ratio for similarity is simply the square of the length ratio. So if you double the length, you quadruple the area. If you multiply the length by 3, you multiply the area by 9. You multiply the length by 5, you multiply the area by 25, and so forth. And if you act right now, I'm even going to throw in a volume ratio. The volume ratio is the cube of the length ratio. So if you double an edge length of a three-dimensional figure, you're going to multiply the volume by 8. Triple an edge length, volume by 27, and so forth. So if you buy my similarity, you will get everything you see in front of you. Everything on the board can be yours. And you're now probably asking me, Anthony, this is amazing. How many easy payments of $19.95 do I have to make to get some of this similarity? And the answer is 0. But you're welcome to send me money if you'd like. I'm happy to give you my address. You can just send me a check. But I do have 3 easy payment plans for this for no easy payments of $19.95. And here they are. For triangles, there are 3 ways you can buy my similarity. You've got side, 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 angle, side, and angle, angle, angle. Side, side, side. If you can show me 3 pairs of sides, each with the same ratio, then you get everything on the previous page. You bought similarity. It's just that basically no one ever buys similarity like this. Why? Because what do you need similarity for at that point? You already know all of the side lengths of each of the triangles. What could you possibly need similarity to tell you? So almost no problems are tested by side, side, side on the GMAT. There is also side, angle, side. If you give me 2 pairs of sides with the same ratio and you give me the angle between them is the same. Now it does have to be the angle between them. If you give me some other angle, I'm like, get that silly crap out of here, come back when you get me a real side, angle, side similarity. But if you give me two corresponding side ratios that are the same, and the angle between them is equal, then again, you get similarity. This is tested a little bit, but it's still pretty rare because it still gives away a lot. I still have to give you two sides for each of the triangles, and at that point, mostly we just don't need similarity that desperately anymore. So by far, the most common way that people buy similarity is with angle, angle, angle. If you show me that all three angles of each triangle are the same, then you get similarity and everything from the previous page. And the great and crazy thing about angle, angle, angle similarity is you can generate angle, angle, angle similarity without even needing to know the angles. Just think back to the problem we just did. I didn't actually know what A and 90 minus A were. I mean, I suppose I knew the 90. But I didn't actually know the angles of those triangles. I didn't need to, because I could say they're the same. This is A and 90 minus A and 90, and that one is also A and 90 minus A and 90. So they're similar. So angle, angle, angle is by far the most common way that similarity will be tested in triangle problems. And we've already seen one way to do it. If you have a right triangle, you drop a height to the hypotenuse, you will create two smaller triangles, and all three triangles, the original and the two new ones, they are all similar to one another. There is another way that is very common to generate similar triangles. And it's another way that I can give you lots of equal angles without necessarily having to be super obvious about it. Rohan, you said, so you only need one angle with each triangle to prove similarity? Well, if you've got two pairs of matching sides, you can get by with only one angle, or you could get by with no angles if you got three pairs of matching sides. But otherwise, you're going to need three corresponding angles to be equal. But that doesn't mean you have to know what they are, right? You might not know what any of them were. In the last problem, we knew that one of them was 90 for each triangle, but it's not even necessary for that to be the case. You might literally know 0 of the angles for each triangle, and all you know is that they're the same as the angles for this other triangle, and that's still good enough. Okay? They just have to match. So think back to the skill builder. And think back, can you remember some place in the skill builder where we learned a way that they could say one little simple thing to you, and like magic, there would suddenly be all of these angles that are equal? Just a whole bunch of equal angles. Can you remember what that was? Okay, equilateral triangles, sure. Not a very interesting basis for similarity. But I'm saying they said one little thing, and all of a sudden you've got like 4 different angles that are all the same as each other, just like magic. In fact, there's 2 sets of them. You guys remember this picture from the skill builder? A pair of parallel lines and another line that cuts them. And you might recall that in this picture, that angle, that angle, that angle, and that angle were all the same. And this angle, and this angle, and this angle, and this angle were all the same. And all I had to do was say the words parallel lines, and like magic, there's all these equal angles. I don't even need to know what they are. I can say they're equal. And here's what I've got to say about that. The words parallel lines, if used in a triangle problem, are a giant alarm bell that this is probably a similar triangle problem in disguise. Okay? They're just trying to give you a whole bunch of equal angles without being too obvious about it. So especially, the more they play it off like nothing, you know, they're like, oh yeah, by the way, these lines are parallel, you don't care, whatever. Like, you know, the more they're just kind of playing it off as like it's nothing, the more they're just screaming, similar triangles! Okay? So look for that. It's a very common thing in these sorts of problems. Now, I'm going to have you do a problem, and this is probably the least surprising thing I'm going to say in the entire course. The next problem is, shocker, a similar triangle problem. And the triangles pictured in this similar triangle problem are similar triangles. No shit, we all say in unison. Having said that, I still want you to go through the process of proving it. I still want you to do the work and see exactly how we can establish that these triangles are similar. And then I would like you to use the fact of their similarity to solve for the answer to this question as easily and efficiently as possible. Okay? Okay. Okay. So I'm going to close this up. We're going to talk about it. Last chance, answers in. Okay. This went well. Although, again, big help if I tell you in advance, it's a similar triangle problem. Let's see if we can prove that. How do I prove that these triangles are, in fact, similar triangles? Can somebody name a couple of angles that have to be equal? Yep, angle, angle, angle. Can you name a couple of angles that have to be the same between the two triangles? Okay, angle D and angle A. Yes. These two angles are both equal because of the parallel lines. This equals that equals this equals that. So this angle right here and that angle right there are equal. Similarly, these two angles are equal as well. And finally, angle B and itself. This angle is literally the same angle in each triangle. So if I call them x, y, and z, x and x, y and y, z and itself, yeah, exactly. You can just literally draw the lines a little farther on your own page. They don't like it when you draw on the computer screen, you know, but on your own page you can redraw the diagram. And here we have it. By angle, angle, angle similarity, these triangles are similar triangles. And we've proved it, right? Okay. Now from here, what is the ratio, the scaling factor, the length ratio for these similar triangles? What is this constant ratio of lengths equal to? It's 2. It's 2 to 1. It's 10 to 5, you know, so it's 2. Okay. What is the area ratio? 4. The area ratio is simply the square of the length ratio. If the length ratio is 2 to 1, then the area ratio is 4 to 1. And if the large area is 40, then the small area is 10 it is. Note that it was not necessary for us to calculate the heights of either triangle. You can. I mean, if you want, you can calculate that the large height is 8 and the small height is 4, and you can get this answer that way. But why? Why would you be wanting to do that to yourself exactly? Make your life as easy as possible. Once you've got the length ratio, square it, get the area ratio, and divide by 4. Similarity is really great. I love similarity. If you've got it, it's such a powerful tool that once you establish similarity, usually you can go straight to the answer within like another step or two. Like it's just going to take you right there. Any other thoughts here? There's not a whole lot more to it done, but just know that the area ratio is always the square of the length ratio. Now, if you might say, why is that? Well, because when I, let's say, double the base, I double the area. But when I then double the height, I double the area again. So if I double the base and the height, I multiply the area by 4. If I triple the base, I also triple the height. I multiply the area by 3, and 3 again, I multiply the area by 9. So I hope that intuitively that explanation makes some sense. It's not a formal proof, certainly, but I hope you can look at it and go, I get why it would square. Right? Areas square units, it's 2 dimensions, and each dimension has been multiplied by this length ratio. So then if the length ratio is 2, then the area ratio is 4. And if the large area is 40, then the small area is 10. Done. Is that sufficient? Does that help? Or okay. All right. If you require a formal proof, or if anyone does, you can email me after class, and I'll give you a formal proof. Okay, we can go through it. I'd rather not, but if you really need one, just email me. Okay. So that's what I had in the triangle section, and conveniently, this is a perfect time for a break. So let's do that now. I'll see you in 8 minutes. Bye, guys. Alrighty. So let's talk about quadrilaterals, shall we? Good news. There's not that much to know about quadrilaterals and other polygons. Yes, there's a whole page worth of memorization stuff, and I hope you have already memorized it from the skill builder, and if not, here it is again. But the thing is that there are a few quadrilateral problems that just in a very basic way sort of test this whole areas base times height deal. And then mostly the rest of them are just triangle problems in disguise, okay? So there's really not that much to say about them, except do watch for triangles, do look to break them down. And by the way, if you get some weird polygon, you get a hexagon or a heptagon or something that says, what's the total angle measure of a pentagon? And you're like, curse Anthony, curse Veritas, they never told me anything about the angles of a pentagon. I'm going to fail my GMAT because they didn't teach me about pentagons. Come on. Whatever. Draw yourself a pentagon. Draw a couple of diagonals. How about that one? How about this one? Oh my god, it's frickin' triangles. Oh look, that triangle adds up to 180, and that's 180, and ooh, that's 180 as well. And you add up all those 180s, 540. The total angle measure of a pentagon is 540. If you get something that's some weird polygon, break it into triangles. Work with the triangles. Okay? It's probably just a triangle problem in disguise. Okay, so let's skip that one. Let me see, which one do I want to, hang on. Shoot. You know, I wanted to do the one after this and then come back and do this, but oh well. I'm sorry. Don Myriagon? What? I'm so confused. What is a Myriagon? Is that a dragon? I have no idea what's going on. Completely lost. Let's just do this problem, okay? Polygon with 10,000 sides. All right. News to me. Basically, at that point, you're just looking at a circle, pretty much. Okay, so yeah, here you go. Here's a problem involving quadrilaterals. Yes. Sorry. I misset the timer, so we're going to stop it when it hits 6 minutes. I know. I set it for 8. I'm aware. You got 17 seconds, okay? Thank you for pointing that out to me. Okay, so we have now hit what should have been 2 minutes. Please get your answers in. I am going to close the poll shortly. Although, you know what? A lot of people are having some difficulty picking answers. I'll give you till the 5-minute mark. That'll be 3 minutes. When it hits 5, I really am closing the poll. I'm closing the poll now. There you go. Now I'm going to reset that back to 2 minutes for the next one. But okay, so let's talk about this problem. So you're standing in the store going, why am I buying a square television, right? Like, who buys a square television these days? I mean, no one's used a square television since, what, the 70s? I mean, are we kidding? Everyone's all about the widescreens these days, the super widescreens. So this problem is dumb, but oh well, I can't do much about that. But at least we can buy a big television, right? Let's all buy the big TV. But how much is 2 inches, really, you're thinking? Well, let's see. It's a 91-inch diagonal or an 89-inch diagonal. So they basically look like this. Now, did you all recognize the special triangles here? Did you all recognize that you're dealing with a 45, 45, 90, x, x, x root 2 special triangle? And that's the thing you're supposed to leverage from geometry. Remember, one thing you know from geometry, one thing they gave you. What did they give you? They gave me the diagonal length. What do I know from geometry? I know the diagonal length. Rub those suckers together. X root 2 is 91. Y root 2 is 89. Okay? This allows me to solve for x and for y. Simply divide by root 2. X is 91 over root 2. Y is 89 over root 2. But don't rationalize, okay? One mistake that a lot of people make here is they're like, oh, okay, I need to multiply by root 2 over root 2, rationalize my denominator is 91 root 2 over 2. If you do that, you're only making your life worse, because think about what you need. Think about what you want. Don't go rationalizing until the last step of the problem unless you have a very good reason for it. Because I'm interested in the areas, right? And how do I get the area? Well, I take the side length of the square and I square it. Maybe that's why they're called squares. Ooh, interesting. And when I square it, that root's going to cancel out. So I don't need to sit there and rationalize something that I'm just going to end up canceling the root off of anyway. Now when I square 91 over root 2, I get 91 squared over 2, and similarly y squared is 89 squared over 2. And now all I really need to do is get the difference between the areas of these two squares. So exactly how, without doing ridiculous calculation, do I get the difference between the areas of these squares? Anyone? Y'all did come back from the break, right? Oh, you use the difference of squares formula? Maybe that's why I kept saying the difference between the areas of these squares. It was a giant hint. Did you all recognize the special quadratic in this problem? Did you all see that there was a special quadratic here? Everyone? Did everyone immediately look at this and go, wait a minute, that's 91 plus 89 times 91 minus 89. And this is exactly what I was saying before. I told you that these special quadratics would come back, but I also told you that the real test was when nobody is telling you to look for them, right? This is the real test of it. If you can't see it when I'm not saying, hey, think about special quadratics, then it's no good to you. If you did not see this here, please go back to the special quadratics, do another hour or two on them, get it to a point where it is absolutely crystal clear for you to spot these suckers whenever they show up on your test. Because you absolutely have to look at that and see the special quadratic. And know how it factors. Spot it, switch it, expect an easy problem. 91 plus 89 is 180. 91 minus 89 is 2, which is super convenient because they cancel. I'm left with 180 is the answer to this question. So, moral of this story, Buy the big TV, am I right? Bet you didn't realize when you're standing in the store thinking about it, that 2 extra inches of diagonal, that's an extra 180 square inches of viewing pleasure. Buy the big TV. Yeah, everyone likes a big television. Also, know your special triangles and your special quadratics. This problem was exactly as easy or hard as whether you knew those two things. If you knew your special triangles and you knew your special quadratics, piece of cake. If you didn't, it's pretty painful. What are your thoughts? I did not have many right answers on this problem. It's true, you could also estimate this. But I actually think you're best off just to kind of do it. This one probably a little harder, maybe 650 or so. Maybe, yeah, I don't know. Sure, no problem. What is it that you're missing? Where are you having trouble, Chloe? Is it somewhere in here? This is the place where most people, I think, have a little difficulty with the algebra. Where did the 180 come from? Well, I've got this difference of squares here, and it factors as 91 plus 89 times 91 minus 89. And 91 plus 89 is exactly 180. Does that answer your question, Daniel? Daniel? Yeah, they are, right? They're absolutely multiplied by each other. So I've got 180 times 2. But don't forget I'm also dividing by 2. This is not negative 180 right here. 91 minus 89, this is 2. Right? So I've got literally 2 there. And I got 180, and then the 2's cancel. There we go. Okay, that's the O I was looking for. Okay. Anything else on this one? Other thoughts? Where did I lose people? This was not good in terms of the results. I did not have enough right answers here. What happened? Was it special triangles, special quadratics, got lost in the algebra? The root 2 on the bottom, couldn't really figure out what to do with that? Yeah, if you rationalize too early, it makes it harder. It's doable even then. Like, it's not impossible, it's just much harder. Didn't divide by 2 because you overlooked it as a square. Yeah, see, everyone assumes rectangle because, like, who buys a square television, am I right? Everyone's like, what's the dimensions of this weird television screen? And they're all confused by it. You know, like, I don't know, how can I do it? I don't know the dimensions. I don't know the ratio of the base and the height. It's so weird. Yeah. But that's why this problem literally says the word square 3 times. Because it is weird, but it does want to make it very explicit. So you just had to really catch the wording there. Okay, so it looks like a few people just mostly didn't get off the ground at the very beginning. Anyone else? Daniel's typing. Automatically wrote down a rectangle. Yeah, they say television screen, and you're like, okay, how wide a widescreen can I get? You know, that's the name of the game these days. Who's buying square televisions? I really don't know. These people, apparently. Okay, so read carefully. Make sure you take what they gave you, even if it's weird, even if it's not your outside expectations. What they gave you is the law. Let's keep moving. Honestly, you know, I think I just want to kind of do this, just the one that we did on quadrilaterals. I think I'm going to go ahead and, well, I'll give you a choice. Do you guys feel like you need another quadrilateral problem, or do you want to move on to circles right now? So in other words, a little more time on circles or a little more time on quadrilaterals? Which one? You can't answer yes. Okay, yes, people are saying yes, quadrilaterals. Okay. Okay, one more. This one should not be as hard, I hope. I guess we'll find out. Okay, one more on quadrilaterals, hopefully not as bad as that last one. Let's do better. And I will also do better by actually sitting the poll for 2 minutes. Okay, so I'm going to go ahead and close this one up now. We're over the time. Answers in, please. Okay. So look, this one again, I think most of the challenge is properly processing what they're telling you, right? The wording is the biggest challenge here. So what you need to understand is that the road is inside the border. So I have this large rectangle that is 60 by 80. And I can get its area very easily. What is the area of the entire plot of land? Yeah, it's length times width, base times height, call it what you like, 4,800. Now, what are the dimensions of the plot of land that is not the road? What is this? What are the dimensions of this smaller rectangle here? Right. The important thing to note is that the road has a width of 5 on both sides. It's 5 there and 5 there. So I don't take away 5 from the 60, I take away 10. That's 50. And similarly, 5 there and 5 there comes off the 80, making it 70. 50 by 70 is 3,500. So my total is 4,800, but I'm taking out the smaller rectangle, and all that's left is the road. And that's B. So what's up? OMG, says Gabriella. I'm sorry, what went wrong? Don't get mad, get even. Just, You know, punch yourself in the face a few times. No, I'm just kidding. I'm joke. Don't do that. But just get better, right? Just learn from it. You know. Yeah. See, the key is right here, entirely contained within the property. Yeah, a lot of people misread this one. Kind of like the last one, they can't really make the math of quadrilaterals all that hard, so they just have to rely on you not properly understanding it. You know, not visualizing right, not getting what they're saying to you, because otherwise it's easy. A lot of people look like they did that. Lots and lots of you, it looks like, went with yeah, let me see if I had done 70 by 90 and then subtracted 6,300 minus 4,800. Yeah, a lot of people went with D here. 7 of you made that exact mistake. I don't know. I mean, I don't know about this one, Matt. I check it on GMAT Club and see what they say about it. I don't always do this. Sometimes I skip it, but I don't think the math of it is that hard. It's just the reading of it. Okay, well, I hope we learned from it. Did you learn from it? Do you feel better about it going forward? If you got another one, would you read it more carefully and get it right? Okay. All right, that's what I want to hear. Let's move on to circles now, okay? Quadrilaterals were a little bit rough. Hopefully circles will go better. And look, if triangles are the #1 thing to know in geometry, and they are, hands down, clear #1, but circles are the clear #2, okay? So if you only know one thing about geometry, let it be the triangle page. If you only know 2 things, let it be that and then this. It is very important to know the basic properties of circles, excuse me. I'm still stuck on triangles. Obviously, you should know what a radius is, what a diameter. You should know what an arc is or a chord. An arc is a piece of the circumference. A chord is any line that touches and connects 2 points on the circle. Note that the diameter is the longest chord in the entire circle, and the diameter is a chord, just a very fancy one. You should know what a tangent line is. You should know that a tangent line touches a circle, and at that point, it is at a right angle with the radius that goes to that point. This means that anytime I say tangent line in a circle problem, I am most likely hiding a right triangle problem in disguise. Okay? It's just, I want to be not so obvious about it. I want to kind of play it cool. You know, I want to give you a right triangle problem, but I don't want to make it super clear. I'll just kind of give you a circle and I'll say tangent line, and haha, right triangle problem, there you have it. You should know the formulas for area and circumference and arc length and sector area as well. Now, I want you to look at these and recognize that they're intuitive. I want you to look at the arc length and go, well, of course that's what it should be. The total angles of a circle is 360. So what am I really saying here? I'm saying the arc length is just a piece of the circumference, right? How big of a piece? Well, what fraction of the circle you got there? What's your angle divided by the 360? You got a 90-degree angle, 90 over 360 is a fourth. You've got a fourth of the circle. I'll take a quarter of the circumference, please. And the same thing with sector area. The sector is a piece of the area. How do you get it? You take the whole area and you tell me how big a slice of pie you want. Okay, does anyone have any questions about the skill builder stuff that is on this page? Does anyone want to hear the worst joke that I know? Okay, so yeah, before you get murdered, don't get murdered, okay? You guys can do this. No, it does not involve dog poop. Okay, this is horrible. You guys are all going to groan. This is bad in a whole different way. I'm actually going to tell you the story of how I heard this joke, okay? So this is not the joke. This is a true story of how I heard it. So when I was in college, I was a math major. You know, I went to Georgia Tech, and I lived on campus. But I would go home from time to time to visit my family, and my parents had this next-door neighbor, this old retired minister guy, and his name was Mr. McKay, and he was the worst. Anyway, every time I would come walking down the street to my parents' house. Mr. McKay would always be standing out in his front yard, and he'd go, "Oh, hi, Anthony." And I go, "Hi, Mr. McKay. Oh, you're over there at Georgia Tech, right?" "Yeah." "You're a math major, right?" "Yeah." So what are they teaching you guys over there at Georgia Tech, huh?" "Math." "Yeah? Yeah? They teach you guys the area of a circle over there at Georgia Tech?" "I guess." "Okay. So what's the area of a circle, huh?" "It's pi r squared." "No, they're not. They're round." "Come on, people. Pi r not square, pi r round." I told you. I love how, like, gradually people get it, and there's probably a few people going, "Wait, I don't get it," right? So anyone here still doesn't get it? Pi r not square, pi r round, yeah, Mr. McKay. I'm glad you like it. I'm glad you like it. So anyway, now you will never forget that the area of a circle is pi r squared, although you will probably wish that you could, right? Because every time you're going to remember that horrible joke. But there you have it. Pi r squared? No, they're not. They're round. Okay, but I'm less interested in the rules. As you know, I'm more interested in the strategy. So what are our strategies for solving circle problems? Well, here's a few. First of all, don't be afraid to draw extra lines in your circle, because understand that the test makers will draw every line in the circle that they, strictly speaking, have to draw in order for the problem to be solvable. But they go out of their way not to draw in certain lines that you will need to use in the process of actually solving it. Therefore, make sure you redraw it on your page, because again, they really don't like it when you draw on the computer screen. And when you redraw it on your page, draw it big enough, okay? Don't draw it like this, okay? Because I get people drawing their circle like this, and it looks okay right now, and they put in a couple lines, and that's fine. They put another line, they start labeling things, and that's R, and that's R, and that's whatever, and that's this, and that's that, and they put in that, and that's 60, and then what? And now you're looking at it like, the hell? I can't do anything with that. So draw it big enough, you know, kill a few trees for GMAT success, except they're plastic trees, so who cares? They're not even real trees, they're just oil. Kill some oil for GMAT success if that's what it takes. But draw it big enough that even when you fill in that information, you can still see it very clearly. Because I've had multiple times where students have just missed problems because they couldn't read their own handwriting because they were squeezing stuff in teeny tiny in their diagrams. And I think that's just such a tragedy. Now, when you draw extra lines in your circle problem, what kind of extra lines do you think would probably be the most important? Well, it's been sitting on the board for a minute, so you probably just read it off the board, but yeah, radii, especially radii. Why radii, even more so than diameters? Because every single thing that we know or might want to know about a circle is given in terms of the radius, all of it. You want the area, the circumference, how about the arc length? How about the sector area? They're all in terms of the radius. So those extra lines you draw should probably be radii, because that's the thing you're going to want to get pretty much no matter what they're asking you for. So don't draw a bunch of random lines. I see people all the time just drawing random chords in a circle, and I'm like, okay, I wanted you to draw extra lines, but what's the point of that? What is that even doing for you? It's a chord to nowhere. It doesn't help. Draw extra lines, they should be radii. They should be radii to points of interest, points that they gave you. And when you draw these extra lines, you are very likely to see triangles, because as I've been saying all along, triangles are kind of where it's at as geometry is concerned. Now, if you were to do this, if you were to draw extra lines and see triangles, then given that these extra lines you drew are probably radii, what kind of triangles do you think you are likely to be looking at? Isosceles, because all of the radii are equal, right? It's fundamentally the definition of radii that they are all the same. But of course that means that if you do draw a couple of radii and end up with a triangle, at least two of those sides will be the same, maybe equilateral. But understand that many, many circle problems are simply isosceles triangle problems in disguise. Sometimes the circle almost doesn't matter except to establish the isosceles triangles. It's only there for that purpose. So really pay attention to that. You'll see this happen a lot. Finally, all the usual strategy things, label your unknowns, be prepared to do algebra, etc., etc., etc. Okay, so I think I've said enough now to get you to a problem and give you a chance at some of these strategies. Any questions before I do? No? Go ahead. Here's your problem. Okay, guys, let's see how we did here. First thing you gotta do, and I mean you gotta do this, you gotta draw these radii. You can't do this problem without drawing these radii. Now when you draw those radii, you see a triangle. And as you can probably guess from this statement right here, it's an isosceles triangle because all the radii are equal. Now, as an isosceles triangle, the opposite angles are equal. I can call them x and x. And let's see. Statement 1 tells me the length of minor arc AB is 1/6 of the circumference. What is that telling me? Exactly, 60-degree angle. Remember that the arc length is just a fraction of the circumference. And the fraction is your angle out of 360. Your angle is 1/6 of the circumference, so your angle is 1/6 of 360, which is 60 degrees. So that angle is 60 degrees. And of course, the other two are equal. What are the other two angles of this triangle? also 60. So wait a minute, this is not just an isosceles triangle, it's equilateral. Ooh, look at that. But I still know no lengths. I don't know a single length anywhere in this picture of anything. So can we all agree that while this statement is very interesting, it is not ultimately sufficient standing alone? Do we all agree that this is insufficient? Yeah. Especially when I hear from those of you who picked D. Do you see why this is not actually a sufficient statement by itself? Well, let's look at the second statement. I don't know yet. Hold on. The length of chord AB is 8. Standing alone, what does this tell me? Nothing. This is just some random chord, right? This does not tell me anything useful. So I guess I'm a little confused about the people who picked A, but I'm even more confused about the people who picked B, and really that means D as well. So the 5 people who thought second statement alone was sufficient, what happened here? Tell me about it. Let's talk. Again, no judgment, but I do want to understand so that we can get it straightened out. Remember, as you're doing statement 2, you don't have the information from statement 1. You don't know that this triangle is equilateral. It is isosceles, but this is not one of the equal sides. Those are the equal sides, and the 8 is just some other side. So, what went wrong? People who picked B and D, what was the thinking here? Cameron, talk to me. Yeah, don't make assumptions. My standard for geometry is always, if you can't prove it, you can't use it. That chord could be very big, very small. I don't really know, you know? I mean, maybe the chord looks like this and it's 8, or maybe the chord is very, very narrow and it's 8, you know? Maybe it's very wide and it's 8. Like, I don't really know what that chord actually looks like. So, without more, this is just not going to work for me. Sorry. So I guess maybe, is that true for the rest of you? Did you just get caught guessing? Did you just sort of assume without proof that if I knew a chord, I could probably get the radius? Yeah. Okay, so the good news here is you just don't have that many things that you know. And again, I've been saying this since day one. That's good news. If you can't make it work with the stuff you know, it can't be done. There's nothing else out there, okay? You know, this is all there is. So don't sit there assuming, oh, there's probably some bizarre rule of geometry I don't know about that's going to give me this. If you can't make it, just assume you can make it. I want to say this, too. I understand why. Okay, I understand why you'd look at a problem and say, well, I can't do it, but it's probably doable. Because when you start out, that's true a lot. There's a lot of things you couldn't do that were nevertheless doable. And it was probably a fair assumption that if I present a problem to you and you couldn't do it, that that was little indication that it's not doable. But as you improve and as you learn more of these rules and you learn more what's out there, you have to be able to shift that expectation as well. Maybe before this class, maybe before everything, it was a fair expectation that there were lots of things you couldn't do, and so it's not real meaningful if you can't do it. But you know this stuff now. You have the tools. You're capable. And so you do need to start getting to that assumption that if you can't do it, then it's just not doable. It just can't be done. If you can't specifically show me how this 8 gets you to the radius, maybe it's because it doesn't, you know? And that'll come with feeling a little better about yourself, right? The more that you trust your own mathematical ability, the more that you're going to look at this and say, well, if I can't get to the radius, then it's just not going to be B. So hopefully you're going to get that place where you can start to feel good about yourself, because actually once you do, and for good reason, I think then that's going to get you more right answers. That's a little weird. I don't know if that made any sense to anyone. Did that make any sense at all? I don't know if I articulated that very well. And no one's talking, so I just feel weird up here now. Awkward. Okay. I hope that made sense. I hope at least one person thought that was insightful or something. Whatever. Let's continue to the statements together. When I put them together, I have three sides that are the same. It's an equilateral triangle. And, hey look, that one's 8. But of course that means those other ones are 8. And those other ones are called the radius. Now I know the radius is 8. And once I have that, I win. Getting the radius is pretty much an auto win in basically every circle problem. Very few exceptions. I got the area. Ding, ding, ding. The answer is C. Okay. Oop. Pen, come on. Okay. Did anyone have any other questions about this now that we've established how to get to C? Questions or comments? No. Okay. Now there's one thing from the skill builder that I think a lot of people... yes, actually, that's a good question, Chloe, and yes, we do. If I back up, let me take a look at exactly what you said. Without statement 1, do we know that those angles are equal? I introduced statement 1, let's see, right here. But before I introduced statement 1, I drew these extra lines, and these extra lines are radii. And as radii, they are equal. And therefore, the opposite angles are equal. And I've got this before I looked at statement 1. So absolutely, without 1, we do know that the angles are equal. Absolutely. It's just that doesn't give me equilateral. It just gives me isosceles, and it's not enough. Okay, good question. I'm glad you asked. So there's this one property, this one theorem in the skill builder about circles that sometimes I think it's a little weird for people. The central and inscribed angle theorem. Do you guys remember the central and inscribed angle theorem? Get a lot of questions about it, usually. Yeah. In case you don't recall, an angle between two radii is called a central angle. In this picture, if O is the center of the circle, X is a central angle. In fact, we can say X is the central angle for the arc PQ. An angle between two chords, like angle Y, is called an inscribed angle. And the central and inscribed angle theorem says two very important and somewhat surprising things. First of all, it says all of the inscribed angles are equal, no matter where I draw this third point. If I draw it there, if I draw it here, if I draw it over there, whatever, does not matter. I know my board's got some bad spots on it. We're working on it. But anywhere I draw it, there, here, here, even over there, even over here, does not matter. All of the inscribed angles for that arc are equal. And they are all exactly half of that central angle X. Now, I think that's surprising. That's a weird thing to be able to know, right? And I was wondering if anyone would like to see a proof of it. Would anyone like to know why that is? Okay. I'm going to show you. No, Alex is like, screw that. Well, Alex, you're outvoted. Sorry. If everyone had said no, I would have skipped it, really. Like, I've had one or two classes where everyone's like, can we just move on? And I'm like, fine, we'll just move on. But lots of people saying yes here, so I'm going to show it. Now, there's two reasons. Oh, Archana's like, oh, okay, no, not similar triangles. Yeah, it's actually not a similar triangle thing, as it turns out. That won't help us here. There's two reasons I want to show this proof, okay? Now, the first reason, I don't know about you guys, but for me, I tend to remember things a lot better when I understand them. If you try and get me to memorize a rule and I don't really understand why that rule is what it is, I am just so bad at remembering it. Like, I will forget. But the minute that I understand why a rule is the way it is, I'm never, ever going to forget it ever again. If you're like me, then I hope that seeing this proof will help you actually remember the central and inscribed angle theorem once you understand it. But even if you're not that way, there's another reason to follow along in this proof, and that is that we're going to use all the same sorts of skill sets that you need to use to solve GMAT circle problems. So while the GMAT will never ask you to prove the central and inscribed angle theorem, being able to do something like that will ultimately help you be better at things that GMAT would ask you to do. So that's why I'm going to show you this proof. Now, in general, I talked about all the same stuff that GMAT generally wants you to do. And one of the big things is draw extra lines. And if you're going to draw extra lines in this picture, what would probably be the most useful extra line you could possibly draw? Exactly. I want to draw a radius. A lot of people want to tell me PQ. PQ is a random chord. It is not useful. It actually doesn't do anything for me. It does not help. The extra line you want to draw is a radius, and it's this radius. Draw that line right there, and your life will get better. You had it right the first time, Archana. Don't let people talk you out of it. OR is the magic for me. Now, when I draw OR, I split my inscribed angle Y into two pieces. A and B, I'm going to call them. Note that I don't make any particular assumptions about those two pieces. I am not assuming that those two pieces are the same. I am not assuming that this radius bisects the inscribed angle. I'm not assuming that the chords PR and QR are the same. In fact, as I've drawn it, I would say it looks to me like PR and QR are not the same, and like A and B are different angles. And that's fine. But I certainly can say that Y is now A plus B, right? Because originally it was Y, and now it's A plus B. Now, what else should we do when we draw extra lines and they're radii? Well, we love to look at triangles. And when we've got a circle, and all of these are radii, and all the radii are equal, we're probably looking at isosceles triangles. What is another angle that I can fill in this picture in terms of either A or B? P, this angle right here, what is this angle? And what is this angle? Exactly. The opposite angles of isosceles triangles are equal. So that is also A, and that is also B. Now tell me, what is this angle right here? This angle. I'm going to assume that's 180 minus 2A, and Alex, you are correct. No, it's not 180 minus A plus B, it's 180 minus 2A. This is 180 minus 2A, and that is 180 minus 2B. Okay? Simply because both of those triangles add up to 180. Everyone still with me? Now, if you're still with me, then let's look at the very center of the circle. There are three angles that make up this complete revolution, and the complete revolution is 360 degrees. So, x plus 180 minus 2a plus 180 minus 2b equals 360. Do you all agree with that? Simply saying these three angles make a 360-degree loop. Now, note that 180 and 180 makes 360, and therefore those cancel out, leaving me x minus 2a minus 2b equals 0. But now, move the 2a and 2b over, x is 2a plus 2b. But actually, that's it. I'm done. Because x is 2a plus 2b But y was a plus b, so x is now 2y. And therefore, the central angle x is exactly twice this inscribed angle. But it's even better than that, because this inscribed angle is arbitrary. I didn't choose r any special way. I just picked a random point. So if x is exactly twice this inscribed angle, then it ought to be twice any inscribed angle for the same arc. And of course, if every inscribed angle is exactly half of x, that means that all of the inscribed angles are equal to one another as well. And that completes the proof. Does it make sense? So you see, even for the big fancy proofs of stuff, what are we doing? Same thing. Draw extra lines, probably radii, see some isosceles triangles, do some algebra. Same stuff. It doesn't really change. These same basic set of tools solve lots of different problems. So if you're thinking, hey man, I bet I get a whole bunch of crazy tools when the problems get harder, no. You actually get just the same set of tools and you just use them in more interesting ways, I guess, but really not much changes. This next problem we're going to do can be solved in at least 2 ways, all right? Now, any way that you solve this next problem, you're going to need to draw some extra lines, and they should probably be radii. But once you do it, you're going to have a choice. Choice number 1 is to do isosceles triangles. Choice number 2 is to use the central and inscribed angle theorem. I don't actually care which way you go. Either one is fine. They're about equally good. They'll get you a solution at about the same pace. Pick whichever one you like for this next problem. Oh, you know, before I give you the next problem, I do have one more thing I want to say. One thing that some people struggle with a little bit is finding corresponding angles, trying to figure out for a given inscribed angle, what's the central angle that goes with it? Or for a given central angle, what are some of the inscribed angles that go with it? I've told you before that I hate the 3-letter notation. This is the one time I'm going to make an exception. I actually really love the 3-letter notation specifically for describing central inscribed angles. Because if you ever are looking at an inscribed angle and you want the corresponding central angle, all you have to do is say the 3-letter name of the inscribed angle. In this case, PRQ. PRQ is an inscribed angle. How do I get the corresponding central angle? Say the 3-letter name again, except change the middle letter to the center of the circle. PRQ, POQ. Inscribed angle PRQ, central angle POQ. Use the 3-letter notation, but just change the middle letter to the center of the circle, and that is your corresponding central angle. That always works. Okay, here's your problem. Again, choice between central inscribed angle theorem or isosceles triangles. I will show both solutions, but you're going to have to pick one of them to do. Okay, I'm taking my time here because I don't even have 10 answers yet, so I assume that maybe people need a few more seconds. And I'm just kind of dawdling, stalling pretty much to give you time to finish up, but I hope you're getting pretty close to finished because I am not going to stall for a whole lot longer. Stalling, 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 staring at the ceiling. I'm up to 14 answers. Okay, one or two more, I'm closing this poll. Okay, guys? Last chance. I'm getting actually close to what would have been 3 minutes now, so pick something, please. Okay. There you go. That's what we've got. Now, however you do this problem, you're going to need to start by drawing extra lines. What are the extra lines that I absolutely positively must draw in this problem? That's right. You must draw the radii OK and OL, because what they want is the length of the minor arc KL. And there's two things you need to get that. One is the radius, which they literally told you. MN has a length of 12, so that means the radius is 6, right? They just handed you the radius. The other thing you need is the central angle for that arc. What angle is that? That's this angle. How on earth are you going to solve for that angle if you don't even have it in your picture? You must draw OK and you must draw OL because KOL is the angle that you need. So no matter what you did, do that first. The other thing you must do, no matter what, is you must give me this 25 here. This comes from the fact that they said those lines are parallel. And this is the opposite interior angle for those parallel lines. And we know that the opposite interior angles are equal. So if that's 25, then this is 25. Now, I'm going to show you two approaches to doing this. And the first one, I don't remember, isosceles triangles. Okay, so name an isosceles triangle that is pictured on the board. KOL is isosceles. Very good, so is MOL. KOL is isosceles. Most people see KOL first. The problem is I don't know any angles of KOL. I don't know the full angle L. I don't know anything about K, and I obviously don't know angle O. That's what I'm looking for. What people don't realize, no, there's actually only two isosceles triangles pictured on the board. There's literally only two, okay? KOL and MOL. Now, there are other isosceles triangles I could create by drawing some more lines, but not with the lines I have drawn. There's just the two. The other one is MOL. MKO is not pictured on the board because I have not drawn the chord MK. So again, there are others I could draw in, but with what I have actually drawn in right now, there are only two isosceles triangles actually pictured on the board. Like you could also say LON is isosceles, even KON, but they're just not pictured. But MOL is the one that people usually miss. And Derek got it. Great job, Derek. Well done. Did everyone see that MOL, this triangle, is isosceles? And what's even better is I know one of the angles of this triangle. Angle M is 25, but that means little angle L is also 25. And now that I have that 25 there, now I can go back to KOL, and since angle L is now 50, angle K is also 50. And finally, if this is 50 and this is 50, then that angle is bingo. That angle is 80. Finally, you've got a formula. Take the arc length. 2 pi r, central angle over 360. The radius is 6, central angle is 80. Plug, chug, etc. Chug, chug, chug. 8 pi over 3. There you go. 8 pi over 3. Got it? Any questions about this approach? Okay. Well, maybe you didn't like this approach. Maybe you just didn't really see that MOL was an isosceles triangle, or you think isosceles triangles are stupid or something like that, and you said, you know what, I'd rather use that central and inscribed angle theorem thing that we just talked about. Fine, let's do it. Once again, draw extra lines, which should be radii. Opposite interior angles of parallel lines are equal. We come right back to this point. Now tell me, angle KLM, this guy right here, is that angle central, inscribed, or neither? That angle is inscribed. That is an angle between two chords, chord KL and chord ML. So it is inscribed. So what is the central angle that corresponds to the inscribed angle KLM? No. No. I mean, yes, it's 50, but what is the name of it? KOM. Again, take the three-letter name, KLM. Repeat it, but in the middle, say the center of the circle. KLM, KOM. This angle right here, now somebody told me the measure of it is twice the 25, so it is 50. KOM or MOK, you guys are right. The people who said MOK, you are correct. That is the corresponding central angle for KLM. KOM is 50. Now, let's look at this angle. Is this angle central, inscribed, or neither? That's right. This is an inscribed angle. LM and MN are both chords. MN is the diameter, but the diameter is a chord. What is the corresponding central angle for LMN? That's right. LMN, LON. And of course, if LMN is 25, then LON is 50. And of course, if that's 50 and that's 50, then guess what? I've got my 80 again, although I got it in a totally different way, using a totally different approach and totally different angles. But it doesn't matter. Same punchline. 80, the radius is 6, plug, chug, 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 8 pi over 3. Does anyone have any questions? Questions or comments? Tanvir? Oh, I'm glad you liked it. That's good. I like this one too. Other people? David? How did I get MOK? Great question. MLK is 25, right? And MLK is an inscribed angle. MOK is the corresponding central angle for MLK. Remember, if you take an inscribed angle, you change the middle letter of its name to be the center of the circle. MLK becomes MOK, and you get the central angle. And remember, the central and inscribed angle theorem says, and I've proven, that the central angle is exactly twice the inscribed angle. So if MLK is 25, then corresponding central angle MOK is 50. To which you go, okay. Okay, that was stupid. Okay. Honestly, I don't have a real preference, Don. When I did this the first time, I found isosceles triangles because I'm probably personally more comfortable with that. But having seen both solutions, I think they're about equally hard, about equally easy. They're about the same number of steps. Whatever floats your boat. Either one. Player's choice. Okay. So that's what I've got on circles. There are a couple more problems that you can go and do on your own. Oh, I should say this. Tell me something interesting about this triangle. I have a triangle here, and it's inscribed in the circle, and BD is the diameter. Tell me something interesting about this triangle. Yes, angle C is 90. How did we know that? This is a right triangle, but how did we know? Exactly. Note that the bad angle here, angle BAD, is 180 degrees, and it's central. What's the corresponding inscribed angle for BAD? It's BCD. And of course, BCD is exactly half of the central. So the punchline here is that if I ever tell you that a triangle is inscribed in a circle, and one side of that triangle is the diameter of the circle, it doesn't even matter anything else. It is a right triangle. And that is important. The GMAT does like to test this. If a triangle is inscribed in a circle and one side is diameter, then it is a right triangle, guaranteed. Guaranteed. We just proved it actually using the central and inscribed angle theorem. Okay. Now, I am going to move on from circles at this point. You guys can go back and do a couple of these other problems. They're a lot of fun, but I don't have time for them in class. Because I am going now to talk about 3D figures and then coordinate geometry. I'm going to be real fast with 3D figures. Yeah, it is handy. I agree. I'm going to be real fast with 3D figures so that I can spend a little bit more time than usual in coordinate geometry, because I know that several of you asked about it. Here's the good news about 3D figures. There's basically nothing to memorize, okay? In fact, there is exactly one formula you need to know for all of 3D geometry, and it's incredibly simple. The only formula you need is that the volume of any 3D figure that they could ask for a formula from you is base area times height. That's it, okay? Consider a cube. The volume is base area times height. How about a cylinder? Base area times height. How about a rectangular prism? Base area times height. Now, what the base looks like changes, but that's fine. You know how to get the base. They're two-dimensional figures. For a cube, the base is a square. So you take edge length squared, and you multiply by the height, which is also the edge length, so it's just edge length cubed. For a cylinder, the base is a circle. Pi r squared. No, they're not. They're round. Pi r squared times height. Rectangular prism, rectangle, length times width. Rectangular prism, length times width times height. That's it, okay? That's the formula. As for surface area, the surfaces are two-dimensional figures. You already know how to do two-dimensional figures. To get the surface area of a cube, you take the sum of the two-dimensional shapes that form the sides of the cube. To get the surface area of a cylinder, you take the sum of the two-dimensional shapes that form the sides of the cube. Cylinder. To get the surface area of a rectangular prism, you take the sum of the two-dimensional shapes that form the sides of the cube. Wait, no, cylinder. Wait, no, rectangular prism. It doesn't matter. You just take the sides that are two-dimensional figures, okay? The only one of these that's even a little hard is a cylinder. But if you've ever peeled a label off a soup can, you know? If you've ever peeled a label off, you know that the shape of that label when you peel it is a rectangle, right? And not just any rectangle. It's a rectangle with height that is the height of the soup can, and that wraps all the way around the soup can when you put it around the soup can, which means that its base has to be the circumference, 2 pi r. So, how do I get the surface area of a cylinder? Well, the top surface is pi r squared, the bottom surface is pi r squared, and the lateral surface is 2 pi r h. Now, Alex is typing question, Alex. Comment? Okay. There are a few shapes that don't follow these rules. For instance, a sphere doesn't even have a base. Certainly, its volume is not going to be base times height. It doesn't have a base or really a height in the normal sense. In fact, this rule only works if your shape looks the same all the way up, like a cube or like a cylinder or like a rectangular prism. They don't get wider, they don't get narrower as you go up. If your shape does get wider or narrower, it'll have a different volume formula. So what you say about those shapes? You said there was only one formula, but you just told me these have something else. The answer is very simple. If you get any other shape on this test, the GMAT will simply tell you the volume formula for it. You are not responsible for knowing any other volume formula. If they give you a sphere or a cone or a pyramid, they will simply also tell you the volume formula if you need it. And if they don't tell you, it's base times height. The same is true for surface area. The surface of a sphere is not something that I can represent as a simple two-dimensional figure. But if they need the surface area of a sphere, they will simply give you the surface area formula. So ultimately, it's just this. Just know this, and if you need anything else, they will give it to you. So what is this about then? It's not really about a lot of formulas. It's mostly about visualization. It's about your ability to see in 3 dimensions. And I understand that that's hard, and some of us may have more challenges in that area than others. So I'll say a couple things about it. If you're somebody who struggles with 3D visualization, the first thing I'd recommend is practice drawing these shapes. I have gotten a lot better at drawing 3-dimensional figures over the years simply because I've taught this class for many years and I have had to repeatedly, over and over, draw these 3-dimensional figures. And as I've improved at that, it's helped me in 2 ways. First of all, whenever I have to do the problem now, I have a really pretty, nice, clear, well-drawn figure to look at. Because I drew it and it was good, you know? Notwithstanding my poor handwriting, I actually draw pretty decent 3D figures now. And that helps me. But also, in all those years, all that process of practicing drawing them, every time I drew one, I had to think about it. And I had to think about what I was representing and how I was representing. And essentially, I was training my brain to be better at thinking about 3-dimensional figures. So not only do I have a better diagram, but also I have a better intuitive sense of what that diagram is actually representing in 3 dimensions. So if this is something that's not strong for you, I encourage you to do the same, to practice drawing them several times until you start to get better at it. The other thing I'll say sounds ridiculous, but I don't mean to be making a joke here. I know I'm always making a joke, but not this time. If you're not strong at 3-dimensional figures, you might consider getting some blocks and playing with blocks. Okay? There are a lot of theories about why some people are better at 3D visualization than others, and actually why there seems to be, and please don't kill me for saying this because I'm only stating science here, there seems to be a correlation with gender about the strength of our 3D visualization skills. Now, why is that? Nature, nurture? Don't know. One popular theory, I tend to subscribe to this one a little, is that it's largely nurture. That certain people are more likely, when they're growing up, to be exposed to geometric games and toys, more likely to be given blocks to play with, whereas other people, and perhaps of other genders, are less likely to receive that kind of thing, and that actually does improve your visualization skills. And if that's true, then that suggests that playing with blocks could actually help you. And my anecdotal story in favor of that is that when I was actually just out of college, but I was dating this girl who was in college, and she was in organic chemistry. She was a biology major, and you may know that organic chemistry is a big weed-out class for pre-med. And the reason that it's such a big weed-out class, in part, is that organic chemistry is the very first chemistry class where the way the molecules behave is not just determined by their chemical composition. It's also determined by their shape. The way that proteins and amino acids fit together matters, and they can take on different shapes even with the same chemical composition. And it's really spatial. If you can't visualize how these molecules fit together, then you don't really know what's going to happen with them. And the girl I was dating was really struggling with that. And what did she do? She bought a 3D, no, she didn't actually. She bought a 3D modeling set and she built these molecules. And she would sit around in our home and she would play with them. And she would just sort of put them together in different ways and she would kind of see how they fit and how they didn't fit. And when she went to take the test, you know, she couldn't take the modeling set with her. But by that point, she understood it. She got it. She could visualize it. And so she did really well, you know, but she learned to visualize by effectively playing with blocks. So if this is not a strength for you, then I say in a very unsarcastic way, that sounds silly, but it's something that I actually believe might help. Now, if you can visualize these and you know just that one formula, there's not a lot else going on. So let me give you one and we'll see how you do with it. And I'm just going to do one and then we're going to move right on into coordinate geometry. These are not a huge part of the test. Okay, here you go. Okay, people, come on. Let's get answers in. Trying to hustle us on to coordinate geometry so we have a few extra seconds there. Anyone else? There's the results. Now, first thing I want to do here is redraw this because this is a crappy picture, okay? First of all, I don't care about the stem of this glass at all. Second of all, I've had a lot of people tell me, like I said, what shape is this glass? And they're like, well, it's a rectangle on top of a circle. And I'm like, what are we, flatlanders? Like, no, this is a three-dimensional glass. It's not a rectangle on top of a circle. Yes, I know they made it look like that. It's because this picture is garbage. And it's not an accident, right? They're not trying to do you any favors. So redraw it and draw it better. Here's my attempt, okay? If I draw it better, I have a three-dimensional figure, and this glass is on top a cylinder, and on bottom, half of a sphere, right? Now, let's start with that. The formula for volume of a sphere, I don't know, except, oh wait, they gave it to me. Ah, good, great. I can use what they gave me. The volume of a sphere is 4/3 pi r cubed, and of course if the diameter is 6, the radius is 3, and I can just straight up plug that in, maybe. Straight up plug that in, but do remember it's not a sphere. It's half a sphere. So I take a half of 4/3 pi r cubed. That's 2/3 pi r cubed, which is 2/3 pi times 27. Chug, chug, chug. 18 pi. 18 pi on the bottom of this glass. Okay? Now, the real trick to this problem is visualization. And the question I have to ask is, what is the height of the cylinder? And how do I get it? And don't tell me it's 7, because it isn't. How did you get the 4? The trick here is that the radius is 3. In every direction. It's 3 this way, yes, but it's also 3 that way. And of course, if I draw that in, then I can split my 7 up into the 3 down there and the 4 up there. So now I know the height of my cylinder is 4. And the volume of a cylinder, well, they didn't give me a formula. I guess the formula must be base times height. The base is a circle. The area is pi r squared. Nope, round. Still round. And I can get it. 36 pi. The total, of course, add them up. That's weird. The pi got green. The 54 did not. That should all be green. 54 pi. I'll fix that later. No problem, Chloe. You were just real excited. I understand. I'm excited too. Does anyone have questions? I had a lot of people miss this. Like, most of you guys didn't get this. What was the problem here? Yeah. And it doesn't work out. You end up with nonsense, unfortunately. Yeah. Yeah. Okay. Couple people got stuck by taking 7 as the height. Somebody forgot to take half the sphere. Yeah, but you see what I'm saying about its visualization, right? Like if you're able to visualize and say, wait a minute, the whole thing's not a cylinder, the height of the cylinder is not 7, and wait, it's not a whole sphere, it's half a sphere, you know, then it's okay. But if you don't have the clear mental picture of what it is you're doing, then it's very difficult. So that's what you need to work on. Okay, let me now move on and go straight past this question, although it's a good question you can certainly go back to. And I want to talk about coordinate geometry. I've got up to 15 minutes of overage time since I always go a little long. Okay. I've already said that geometry is largely a layering mechanism for algebra. But coordinate geometry takes this to a whole other level. Coordinate geometry is hardly a layering mechanism, and it's basically just algebra, okay? Like, let me give you a sense of how much this is algebra. Coordinate geometry is so algebra that in the official guide for the GRE, the coordinate geometry is covered in the algebra section of the official guide, not the geometry section. Like the GRE people, they're like, screw it, this is just algebra. This isn't even geometry, it's algebra, okay? And in the way that it's different from the rest of it is that it's not layering. In most of these problems that are geometry, I start with geometry, and I leverage some stuff, and I end up with an algebra problem. But I go from the picture first to algebra later. In coordinate geometry, I almost invert that process to where usually I don't start with the picture. I start with the algebra. And I may or may not get around to drawing a picture later on, but just as often, I don't. Just as often, I just do the algebra and I've got the answer and I'm done. Okay? So let the algebra lead here and let the algebra guide you, because that's what this is all about, even more so than the rest of this book. So, basics. You should know what the x and the y-axis are. X-axis is horizontal, y is vertical. You should know which way is positive. It's to the right and up. Points are plotted in the order x, comma, y. Lines are a big deal. In coordinate geometry, you should know the standard form equation of a line, y equals mx plus b. Of course, you should know that m represents the slope of the line, which is rise over run, y2 minus y1 over x2 minus x1. B is the y-intercept of the line. It is where it crosses the y-axis, where x is 0. If you want to get the x-intercept of the line, simply plug in y equals 0 and solve for it. Note also that parallel lines have equal slopes. Perpendicular lines have negative reciprocal slopes. So if my line has slope 2/3, what is the slope of your perpendicular line? Again, my line has slope 2/3. Very good. Negative 3/2. 2/3, negative 3/2. Negative reciprocal slopes. Got it? Now, if you ever need to get the distance between 2 points, Don't memorize some fancy distance formula. Simply use the Pythagorean theorem. I will show you an example of that in just a minute. And if you need the midpoint of 2 points, simply average their coordinates. The average of the x-coordinates, comma, the average of the y-coordinates is the midpoint. Okay. Examples. If I needed to get the distance between 7, 8 and 10, 12, I would draw me some coordinate axes, and I would plot 7, 8 and 10, 12. Note, I don't have time for the noise that is drawing all of the little tick marks. Please don't be that guy or girl and draw in all the little tick marks on your page, or even use your graph paper and very neatly count off, 7 and then 10 or whatever. It's so time wasting. It gives you this false sense of scale and all this stuff, and I don't want it, I don't need it. I just go on my page and I'm like, that looks like it could be 7, 8, that looks like it could be 10, 12, plot, about that fast. Now draw the line between them. That's the distance I want. I want the length of that line. Now, drop a height just straight down from 10, 12. Run a horizontal over from 7. Oh my God, it's a triangle. Holy cow. Wait a minute. It's not just any triangle. It's a right triangle. What is the base? What is the horizontal distance of this right triangle? Yes, Chloe, you're way ahead of us. Very good. What is the horizontal distance between these 2 points from 7, 8 sideways laterally over to the 10, 12? 3 from 7 to 10. And the vertical distance, Alex, I think you're just living a few seconds in the future. Yep, 4. And now, Chloe, you were living a few seconds further in the future than Alex was, because the hypotenuse is 5, because special triangles, hooray. If you ever need to get a distance in coordinate geometry, do this. There's no reason to do anything more than this. There's no reason to memorize a fancy formula. Just do this. Okay? Now, one thing that I know that people have a lot of trouble with, that they trip up on way more than they should, is intersections. Where do 2 points intersect? Like the third example here. Think about it this way. If 2 lines, or frankly curves or whatever, it could be a circle and a radius, hypothetically. I'm not saying there's a homework problem where a line is intersecting with a circle and you need to find the intersection point. I'm not saying there is such a problem. I'm also not saying there isn't. But if hypothetically there were, all I would do is I would get the equations of each of them and I would solve the system. Because in order for a point to be an intersection, it must be on each of these 2 things. And in order to be on them, that means it is a solution to each of the equations. But if it's a solution to both equations, that means it is the solution to the system. So solve the system. Now you know that I generally prefer to solve my systems by elimination. However, coordinate geometry is one of those exceptional cases where I tend to go the other way and I tend to favor substitution. Why? Because most of the equations that I'm going to get in coordinate geometry are in the form y equals blank. Y equals mx plus b, standard form equation of a line. And if you're going to do the work of solving for a variable for me already, well, you've done half the job of substituting, then sure, I'll do the other half of it. And if I had this system here, these 2 lines, I want to know where they intersect. All I would do, let me go down a few slides to where I do this for you. Skipping this one, skipping this one, skipping this one, skipping this one. All I would do is I would plug this in right there. I would just basically be setting them equal. 2x plus 6 equals 4x plus 2. And I would solve for x. And I would then plug it in and get y. I plugged it into this equation, 2 times 2. So I found that x was 2. I plugged in here. 2 times 2 is 4 plus 6 is 10. Do you want to check your work? Of course you want to check your work. Coordinate geometry is great for checking your work. Also plug in x here. 4 times 2 is 8 plus 2. Still 10. Hooray! It really did work. The intersection is a point 2, 10. Does that make sense? I'm going to give you a problem in a minute, but let me ask you guys, because several of you were concerned about coordinate geometry. Was there something specific from the skill builder that you were having a hard time with, something specific that you would like me to address before I give you our last problem of the night. Multiple points to plot? Well, again, what I would suggest is that when people start plotting the points too early, they make their lives worse. In fact, the problem I'm about to give you involves 3 different intersection points. And what I would say is make sure you find them all first, and make sure you do the algebra first. Lead with that, and then you'll get the points. You'll find it, I hope, a lot easier to plot them. So maybe this next example will answer that concern, Archana. Was there anything else that anyone had? Okay. So I would like you now to do coordinate geometry drill number 5. There won't be a poll on this because it's going to be free response, but I'm going to run a timer for 2 minutes. And when 2 minutes expires, and not before then, please shout out the area of the triangle. My suggestion is right here. Set each pair of equations equal to find the intersection points first, and only after that should you try to draw anything. Don't start by drawing these lines. You'll make your life worse if you do. Okay? 2 minutes, and then once the timer's done, shout out the area. Here's some more answers, people. You've had 2 minutes. Shout them out. What the hell? 445,455. Oh my God. Cameron, I think it's probably a little smaller than that. David says 45. Cameron now says 45. Gabriella says 45. It's a big triangle. Okay. Yeah, it's 45. So let's go through how to do it. And that'll be it, because it'll be super out of time. Take the first two equations. Set them equal, right? I'm substituting. What I'm really doing is solving by substituting. But basically what that means is set the right-hand sides equal. 2x minus 2 equals negative 1/2 x plus 8. Move all the x's to the left, all the constants to the right. 5 halves x equals 10. So x equals 20 over 5, which is 4. Plug it back in. 2 times 4 is 8, minus 2 is 6. The point is 4 comma 6. Now note that I plugged in here. Want to check your work? Of course you should check your work. Take that same exact 4, plug it into the other equation. Negative 1/2 of 4 is negative 2. Plus 8 is still 6. It works. It works in both equations, so you know you're right. If you made a mistake and you plugged in both equations, you wouldn't get the same thing, and you would know that you had messed up, and you can go back and fix it. Now, take the next two equations. Take the first and the third. 2x minus 2 equals 0. So 2x is 2, x is 1, 1 comma 0. Now do it one more time. The second and the third. Negative 1/2 x plus 8 equals 0. 1/2 x equals 8, x equals 16, and you get 16 comma 0. Now, if you wanted to draw the lines and the points, here's your chance. That's 1, 0. Sure, why not? That looks like that could be 16, 0. Up here, maybe, that's 4 comma 6, something like that. Whatever, close enough. Draw some extra lines, connect them up. Blah, blah. Oh my god, it's a frickin' triangle. What do you think, Archana? I know you were asking about something like this. I hope this answers your concern a little bit. Base of the triangle is 15. Height of the triangle is 6. Area of the triangle is 1/2 base times height, which is 45. And that is exactly how I would do that problem. Does anyone have any final questions, comments, thoughts, feelings, emotional outbursts? I know today was a little rough. I hope you've learned from it. I really do. What are your thoughts? Gabriella or Tanvir? Matt? Tanvir? Gabriella? Anyone? Need to keep drawing it out? Okay, but do the algebra first. Algebra first, draw it second. If you try and draw it first, I just don't think it's going to do you any favors. I see too many people, maybe don't do a great drawing, end up confusing the issue. Okay. Well, that's all the time I got for tonight, so I will see you guys all next week. Just a programming note, when we do reading comprehension next Monday, that is when we're going to catch up the ratios and percents from the arithmetic lesson. So be prepared for that. We're going to do reading comprehension and the ratios and percents from book 2 on Monday, and I will see you then. Have a good week. Bye, guys.